The system that we use to review the classical treatment of a mass orbiting the origin can also be associated with a quantum mechanical system. Since there's no potential function, we can write the Hamiltonian in this case as simply being equal to negative h bar squared over twice the mass times the sum of the two second derivatives. And I probably should make these partial derivatives because we have more than one variable. All right, so this is exactly the way we started with the classical mechanics, and I'll note over here that this is with a constant distance r from the origin. So again, the Cartesian coordinate system is not the best system for us to be working in, and we need to make a change to the plane polar coordinate system. Now I've written out some identities for the plane polar system here, and I'll just label this down here at the bottom as the plane polar coordinates. So we have x is equal to r cosine phi, y is equal to r sine phi. We can also write r and phi in terms of y and x, which are done here in the second panel. And then we need to use the chain rule to change our derivatives. So for example, if I have d dx, I need to change that into a combination of r and phi. So I'll need dr dx at constant phi, ddr plus d phi dx at constant r, d phi. And I've got the appropriate two derivatives here, so I can simply write this down as equal to cosine of phi ddr minus sine phi over r d phi. Now once again, r is being held constant, so I can get rid of that term. I don't have to worry about that. I can do a similar result for d dy, and that will be dr dy at constant phi ddr plus d phi dy of d phi at constant r. And now I'll get sine of phi ddr and plus cosine of phi over r d phi. Now I've gone through this not because it's so important that you know this, but I want you to see how to think through this when you need to change from a Cartesian system to a plane polar coordinate system, or even a spherical polar coordinate system, as we'll talk about later on. All right, so what we want to do is we want to take the squares of each of these operators, because they exist here in the Hamiltonian, and rewrite them in terms of our plane polar coordinates r and phi. So if I do that, I have d squared dx squared plus d squared dy squared. It's going to be equal to this combination of things. Now I'm already getting rid of the ddr because r is constant in all of this. So this is going to make it actually quite a bit easier. So I just need to take the square of this term, which will be sine squared over r squared d phi squared. That's for the x term. And for the y term, I'll just take the square of this. So I'll have plus cosine squared of phi over r squared d phi squared. And once again, sine squared plus cosine squared is going to equal to 1, so I'll have 1 over r squared d phi squared. And that's really what's going to be in my Hamiltonian up here at the end. So now I have a fairly simple Hamiltonian. I can write it down here as Hamiltonian is equal to negative h bar squared over 2 m r squared, because the r squared here, d phi squared. All right, and that's it for the Hamiltonian. So now if I recognize that this is the moment of inertia, I can write this as minus h bar squared over 2I times this second derivative in the angle. And now I can create a Schrodinger equation out of this as follows. I'll have minus h bar squared over 2I times the second derivative of the wave function is equal to the energy times that wave function. And that should be a capital phi there. Okay, so this is my Schrodinger equation for this simple particle in a ring system. And this should be a very familiar equation at this point. If I move this set of constants over to the other side, I'll end up with the fairly simple second-order differential equation that looks like this. Right, and this is one that's very similar to the ones that we've seen before for the classical wave equation. All right, and we'll note that if this is the constant here, the moment of inertia is always a positive number. In this case, the energy is going to be a positive number. We have no potential, and h bar squared is a positive number. So this could be written as minus m squared times our wave function phi. Okay, so this now directly is something that we've seen before, and we can immediately write the solution down. I hope we can immediately write the solution down as the wave function is equal to e to the I m phi. Now, in this case, m could be any number. We haven't restricted it at all. But notice that because this thing is rotating in a circle, I must have the condition that when you've gone through by 2 pi radians, that it brings us back to our initial point. So in other words, I must have this as my boundary condition on the solutions of this problem. So when I plug this into this form, I'll end up with this. I'll have e to the I m phi plus 2 pi is equal to e to the I m phi. Now I can rewrite this as I m phi times e to the I m 2 pi. And when I do that, these two terms are the same, so I get that e to the I m times 2 pi must be equal to 1. And the reason this doesn't seem like it's very cosmic, but the reason this is important is because it tells me that the values of m that are allowed are just the integers. I can't have non-integers for my m values. So the fact that we're restricted to integers also is going to restrict our values for the energy, because remember, the energy up here, this m squared, was equal to 2I times the energy over h bar squared. So I'm going to use the next sheet to finish this out. So now when I write down the energy, I've got, negative 2IE over h bar squared is equal to negative m squared. So if I solve for the energy, and I'll use a subscript m to indicate this, it's going to be h bar squared m squared over 2I. And m is equal to 0, 1, 2, and so forth. And then also the negative versions of those. All right, so this gives us basically the energy levels that we should expect to see in this particle on a ring model. And I'll note that these are actually pretty similar to ones that we saw for the particle in a box. Remember that the energies for the particle in a box could be written as follows: h squared n squared over 8ml squared. So we want to compare that now with the ones that we're finding for the particle on a ring, which is e to the m h bar squared m squared over 2I. Okay, so once again, and remember the 2I has got mr squared, so it's very much like the thing we have in the denominator for the particle in a box. What's the difference between these two? Well, the difference really is that for the particle in a box, we had boundary conditions that said that the wave function at 0 and the wave function at x equal L were both equal to 0. So that was a very fixed boundary condition. For the ring, however, they're not both equal to 0. They're actually equal to one another. So I should say the wave function at angle phi is equal to the same wave function at angle phi plus 2 pi. So this difference in the two wave functions is all that accounts for the difference between these two values, and basically allows m to be any of the integers here, whereas in the particle in a box, we could only have positive integers as our quantum number. All right, we'll be talking more about this system as we move along and look at more complicated systems too that will give us a little bit more insight about the role of angular momentum.